All right, so here we go with part 3 of section 5.2. We're going to take a look at finding a sum of an area under a curve, but I don't have a curve. I have data, right? And my job is to find the midpoint sum. Now, don't worry about this name Riemann. Riemann is the fancy name for what we give to this process. Okay? All right, so instead of having a curve, I don't have a function to work with where I can say find this area. I don't have that. What I have is I have data. And so I have points that I can plot. But I can still take points and turn points into rectangles. Now, there is absolutely nothing about this process that ever requires that the intervals down here have the same width. Right? We make them all have the same width when we can because it makes the process easier. But there's nothing about this that says they have to or they need to. You can use an approximation where you have a lot of wide intervals and a lot of skinny intervals. If you had a function that was kind of flat for a while and then sharply increased, you might want to make one big interval down here, a skinny interval here, and then a bunch of skinny ones to account for that quick increase, because that would make sense geometrically to try to reduce the amount of error. Okay? So what we're going to do here is we're going to make a sketch of this data real quick, and we're going to see if we can somehow figure out what this means to do to use the midpoints with 3 sub-intervals of equal length. Okay? So it looks like my x's go out to 12. So I'm going to put 12 here, which means 6 is about there, so 3 is there. 1, 2, 4, 5, that would be 9, 7, 8, 10, 11. So there's 4, there's 2, there's 6, there's 8, there's 10. Okay, 11, 7, 5, 1. And now I'm going to plot this data. It looks like my y-axis needs to go up to about 150. So then that would be, what, 50 and 100? Okay. Now, given these values that I'm seeing right here, this is not going to be a to-scale graph because there's no way I could do it well. So I'm just going to kind of fudge this a little bit. 0 is 3, so that's way down here. 2 is 7, so that's almost the same. 4 is 19, so maybe we can see that. 6 is 39, so I can definitely see that now. 8 is 67. 10 is 103. And 12 is 150, roughly 147. Okay, so there's my data. Now, if I had a curve, it would kind of look something like this, right? But I don't. I just have these green points. And they want me to find this using midpoints. Now, this idea of using midpoints means the height of the rectangle is determined by the midpoint. And 3 subdivisions of equal length. Okay, so I'm going to start introducing some notation. We're going to use delta x to represent the width of the rectangle. And delta x, the width of the rectangle, when they are of equal length, is always b minus a over n. Okay? Where the left-hand edge we call a, the right-hand edge we call b, and n is going to be the number of rectangles. So then for this specific problem, that's going to be 12 minus 0 divided by 3, which is 4. So that means that every rectangle is going to have a width of 4. So the first rectangle is going to be from 0 to 4, and then from 4 to 8, and then from 8 to 12. And then we're supposed to use the middle of each of these, the midpoint of each of these, to determine the height. So the midpoint of the first rectangle, if it goes from 0 to 4, the midpoint is 2, so that's our height. 4 to 8, the midpoint is 6, so that's our height. 8 to 12, the midpoint is 10, so this is our height. And then these are the 3 rectangles that we're going to add up. Right? So this rectangle, I'm going to call it rectangle number 1. Right? is going to have an area of base 4 times height. The height is the value of the function at 2, which is 7, so we get an area of 28. This second one right here, we're going to call this rectangle number 2. So area of rectangle number 2 is base. Well, the base is 4 times the height. The height is the value of the function when x is 6, so that's 39. Let's see, 4 times 40 would be $1.60. So 4 times 39 is $1.60 less 4, so $1.56. And then my third rectangle over here, rectangle number 3. The area of rectangle number 3 is going to be base 4 times height. The height is the height at 10. 10 is 103, so 4 times 103, which is 412. And so the total area is approximately 28 plus 156 plus 412, or approximate, let's see, 400 plus 1 is 500, so 560, 580, 596. Approximately 596 square units. Right. So I don't even need a function as long as I have enough data. Now this one told me to use midpoints, but I could use lefts or rights or midpoints. It also told me to use 3 subdivisions. If I wanted to, I could have used more based on my data, but I'm limited by the data, right? Since I have, let's see, 1, 2, 3, 4, 5, 6, 7 different data points, I could have broken this up to have widths of 2 and have one rectangle from 0 to 2, another rectangle from 2 to 4, 4 to 6, and so on and so forth. But I couldn't break it up into any number of rectangles. I couldn't break this up into 5 rectangles, because how would I do the heights then? And when I say I couldn't, I'm really lying there. I could, but it would just get ugly. And so to keep it nice, I want to make sure I use a height that's a left or a right or a midpoint, and so I'm limited, right? Whereas with a true function, you're not limited. So here's another example. Find the midpoint. Riemann sum. Riemann is just the fancy name for this idea of doing rectangles. For the function f of x equals x cubed plus 1 over the interval 0 to 4 using 4 subdivisions of equal length. Well, I'm a picture guy, so I'm going to draw this first. I'm going to make a sketch of this thing. I have the function x cubed plus 1. Translated vertically 1 unit on the interval 0 to 4, and I'm approximating this area right here. Right? I'm supposed to use midpoints and 4 subdivisions. So then the width of each rectangle is going to be 4 minus 0 divided by 4, which is 1. So every rectangle has a width of 1. So the first rectangle will stop at 1, the second rectangle will stop at 2, the third rectangle will stop at 3, and the fourth rectangle will stop at 4. And so I'm going to get this. And then how am I measuring heights? I'm using midpoints. So I'm going to come over here and say, well, there's the midpoint, so that's the height. 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 Right? But just simply saying there's the midpoint doesn't really help me. So what I want is I would like some sort of a formula that I could use to generate those. And now I'm going to toss another phrase at you. Sample points. Sample points is the fancy name for whether you're using left, right, or midpoint. And we have formulas. Lefts, the sequence formula for these, and I hope you heard that word because that's where it's going to tie back into summations, is that a sub I is always equal to A plus I minus 1 times B minus A divided by N. Or you will sometimes see it written like this: A plus I minus 1 times delta X, because we define delta X to be B minus A over N. Okay? Rights are always that the sample point A sub I is always left-hand endpoint plus I times delta X. And midpoints the formula is always A plus I minus 1/2 times delta X. Right? You will become very familiar with these formulas in this section. Which one do you think I like the best? If your guess was this one, you are correct. Because I'm lazy, and it's the easiest. I don't want to do I minus 1s. I don't want to do I minus 1/2s. I just want to do I. Okay? But I can do whatever they tell me, because I'm really, really good at this. So if they want me to do I minus 1/2, I can do I minus 1/2. All right, so our sample points. Our sample point, oh, wrong one. Our sample points for this example, our A sub i's, are going to be midpoints. So they're going to be 0 plus I minus 1/2 times delta X, which we already defined to be 1. So our sample points are just going to be I minus 1/2. So our sample point for the first rectangle is 1 minus 1/2, which is 1/2. Our sample point for the second rectangle is going to be 2 minus 1/2, which is 3/2. Our sample point for the third rectangle is going to be 3 minus 1/2, which is 5/2. And our sample point for the fourth rectangle is going to be 4 minus 1/2, which is 7/2. Now I know what you're thinking. I didn't need all this fancy stuff to come up here and look at this interval and go, that's 1/2. That's between 1 and 2, so that's 3/2. That's between 2 and 3, so that's 5/2. That's between 3 and 4, so that's 7/2. And you are correct. I could have done that. But when the math gets more complicated, the formulas become appropriate. All right, so just review. My job is to find an approximation for the yellow area by breaking it up into 4 rectangles and measure the height by using midpoints. These are what we're calling our sample points. Our sample points are the x's that we will use to find the heights. Okay, you ready? Now I'm going to go find those areas. Rectangle number 1. The area of rectangle number 1 is the base, which you decided is 1, times the height. The height is going to be the value of the function when x is 1/2. So it's 1/2 cubed plus 1. Let's see, I don't really even need this 1 out here, do I? So it's going to be what, 9/8 when it's all said and done? All right, rectangle number 2. Area of rectangle number 2, base is 1, height is going to be the value of the function when x is 3/2. So 3/2 cubed plus 1. Let's see, 3/2 cubes is 27/8 plus 1 would be 35/8. Rectangle number 3. The area of rectangle number 3 is base times the height. That's going to be when x is 5/2. So 5/2 cubed plus 1. Let's see, 5/2 cubes is 125 over 8. Plus 8 over 8, that's what the 1 is. 125 plus 8 is what, 133? And then, of course, rectangle number 4, the area of rectangle number 4, is going to be when it's 7 halves. So it's going to be 7 halves cubed plus 1. I decided to omit the base here because it's just times 1. 7 cubed is what, 243? Okay. 243 plus 8. Wait, something's bothering me. It's not 243. 7 cubed is 343. Jeepers creepers, come on. All right, so 343 over 8 plus 8 is what? 351 over 8. Okay. So now the total area is approximately the sum of this. And so I need to take the first rectangle at 9/8 plus the second rectangle at 35/8 plus the third rectangle at 133/8 plus the fourth rectangle at 351/8. And so that's approximately, I'm going to grab my calculator for this, 9 plus 35 plus 133 plus 351, and I get 528 over 8. I think that's going to reduce. It does reduce down to 66. So is this an underestimate or an overestimate? Well, to be fair, the correct answer is I don't know, right? Up here in the other examples we've done, specifically up here, it was very, very easy to make an argument that this was over because all of the rectangles are too big, and that this was an underestimate because all of the rectangles are too small. But as soon as you start doing something where each rectangle is sometimes too big and sometimes too small, sometimes too big and sometimes too small, sometimes too big and sometimes too small, you have no way of knowing by looking at it whether you're looking at an underestimate or overestimate, especially with some horrible hand-drawn graph like this. So I don't know whether this is an underestimate or an overestimate. The only thing I know for certain is that it is an estimate. I am estimating it, and that is all that I'm doing. My estimation for the area under this curve is about 66. If I want a better approximation, what I will do is I will use more rectangles. And as I use more rectangles, my approximation will get better, but also the amount of work that I will have to do will increase. So there's this balancing act that we have to do between enough to make it accurate, but few enough to make it calculatable. All right, I'm going to stop this video here. We'll come back and we will do exact areas of these functions. See you all back here for the next part of section 5.2.